Testing, testing. 1, 2, 3, 4. Testing, testing. 1, 2, 3, 4. Okay, welcome to the machine learning class today. and I see many of you are on Slido now. Before the class begins, I have a few announcements to make. First, we will announce homework 1 today. Yay! Okay, so basically we're done with homework 1. We have a complete version. After class, I will put homework 1 online, and you will have 2 weeks to complete the homework. Basically, the homework will contain 16 problems. Actually, I can, let me see if I can show you that. Oh no, it's hard to show you. Okay, anyway, okay, you will see it after class later, and there will be 16 problems, multiple choice ones, and you need to enter your choice on Gradescope, as well as giving us your detailed solution, okay, for TAs to grade. The TAs will not grade every problem, okay? They will choose 4 of the problems to grade. And basically, those 16 plus 4 counts as total point of 400. Okay, that's the design of homework 1. As always, we encourage you to go to the TA hours to ask TA questions to help you solve the homework. But we also need to remind everyone that you should write the final solution down by yourself, okay, without copying others and so on. You can consult others as much as you want before you start writing down your solutions, okay? But once you understand what the problem is about, how to solve it, and so on, sit down and try to write down the solutions on your own, okay? This is our way to ensure fairness, okay, in terms of grading. Okay, that's about homework 1. And the other thing that I want to announce is that we set up another Discord channel, actually. Okay, so basically, if you go to our Discord server now, in addition to the original channel of general and homework 1, now we have another channel called class. Okay, so what's this channel about? We noticed that many of you are asking questions on Slido about clarifications of some details, okay, like meaning of notation and so on. And Slido does not seem to be a good platform for answering that kind of questions, not for me and not for maybe other students. Okay, so we decide, actually following the suggestion from a student, we decide to give Discord a try to see if it's a better channel that you can use. So during class time, if you believe you want some clarification, possibly less major one, you can try to use this channel to see if you can get direct responses from other students or maybe the TAs if they happen to be online for clarification. Okay, we will see how things go to decide whether we will continue using the Discord channel or if we can have other mechanisms to help be more responsive on this kind of questions. Okay, and I will try to prioritize my time on the bigger questions, okay, on Slido instead. Okay, so basically the Slido questions and the Discord class channel ones would go in parallel. I will not check the Discord ones, but we do hope to create a peer learning environment that people can freely ask questions on Discord and get answers from your peer or maybe other TAs. Okay, so let's give this a try. And of course, we welcome your feedback on how things go. And we still welcome your questions on Slido. If you are not sure whether your question is big or small, you just put them on Slido and I'll just choose. But if you are kind of certain that you just need a quick clarification on the reason behind one of the equations or something, maybe Discord would be a better place for you to ask those questions. Okay, so let's another thing that I want to add. And before we start today's class, let me quickly check if we have any bigger questions on Slido. Okay. Good morning, good morning. Okay, great. Okay, hello and good morning to you too. And now let's begin the first part of the class. Actually, the first part of the class was left over from the previous class. Okay. See? Last time we ended talking about different protocols, okay, that we can communicate with the machines. Okay, we gave you several examples of different protocols that people have considered. For example, batch learning, okay, like duck feeding, just throw your computer lots of examples, okay, in a batch, and then just want your computer to sit there, read all the examples on her or his own, and then learn the knowledge. Okay, the batch of examples can be labeled, okay, like what we encountered in supervised learning, or can be unlabeled, okay, like what we encountered in self-supervised learning or unsupervised learning. Okay. And there are protocols that are online as well. So basically, we let the machines receive streams of data and process or digest, okay, stream data sequentially coming in progressively. And in terms of progressively, we are expecting the machines to update the model progressively and also make predictions progressively. Okay, so that's basically what's behind the online protocol. And as you can imagine, many of the more setup in sequential nature, like reinforcement learning, have a sense of being online. Okay, but usually the online protocol is used to describe something that's more passive. Okay, so we just feed the machine with data. Okay, still like duck feeding, but one by one. While reinforcement learning is arguably more similar to active learning. Actually, one of you raised this question in class last time, where the learner is actively asking questions. Okay, the difference between typical active learning and reinforcement learning is really active learning asks for the exact label, at least in the setting we consider here, while reinforcement learning focuses on combining the decision with question asking. Okay, so the decision of the learner is exactly the question being asked. Okay, so that's how in the reinforcement learning example, the dog, okay, by choosing the action it does, receive feedback from us on whether it is the right action that we want. Okay, so those are like subtle differences. Okay, we are not highlighting that they are significantly different and so on. If you notice, we've put reinforcement learning and active learning in different parts, okay, when discussing about machine learning setup. Okay, but basically, I think the important thing is to understand the similarity and the differences. Okay, not exactly how we categorize those. Okay, according to how they are used in the bigger learning picture. Okay, so that's what we did last time. And this time we're going to start with a new topic that tells us how learning can be different if we consider different input spaces. Okay, if you notice, all the previous variations of machine learning mainly focus on different output spaces, or different output spaces defines different hypotheses or different target functions, that different problems that we want to solve. Okay, and different levels of information in the output space. Okay, labeled, unlabeled, partly labeled, and so on, defines the information that we can get from the output space, from the supervision, and the protocol defines how we get it. Okay, how we get those information. Now, in the input space part, let's think about what can be different. Okay, in the credit approval example that we have discussed, we can see that the factors that we consider, okay, for the credit approval problem are those items that are listed on the application form. And those arguably carry some concrete meanings, okay, or meanings that are somewhat related to the outputs that we're interested in. Okay, so those are condensed information, okay, that are at least somewhat related, okay, to the task of interest, okay, or we say they carry some sophisticated physical meaning. Well, if you look at some other problems that we have considered, for example, for coin classification, we say, okay, we can represent the problem, represents the inputs by the size and the mass of the coins that we have on hand. Okay, we're not measuring the coin by every detail. We summarize the property of the coin, or sometimes called the features of the coin, okay, by two values, okay, one called size, one called the mass, okay. And if we look at cancer diagnosis, okay, doctors may know what questions to ask the patients, okay. Those related patient information are concrete features that carry physical meaning, that often includes some human intelligence about what's related to the learning task on hand. Those are what we have considered, or we call them the easy ones for machine learning. Okay, those are the easy tasks. We know how to form those if we have a little bit of human intelligence towards the problem. Okay, and we put them into our learning framework, and then machines can carry from there. Those are the easy ones. Now, what are the other ones that we want to talk about today? Let's think about one very typical problem that we will encounter in machine learning nowadays: digit recognition. Okay? We mentioned that recognition is a very typical problem in machine learning, okay, and also a very intelligent behavior in terms of doing computer vision. And to recognize the digits, what we want to do is for the machine to map from the features, okay, of whatever that image to the meaning of digits. Okay, if we gather many digits and also label them, okay, with whatever category they deserve to be, then this is a classical supervised multi-class classification problem. Actually, this problem drives the very first deep learning model that you see nowadays. Okay, that we will discuss a little bit more later, but you should know that this written digit recognition problem was so important, okay, that one of the deep learning pioneers, nowadays Yang LeCun, designed a deep learning model to solve this problem many years ago, even before deep learning became hot, and that's called the convolutional neural network. Okay, so how do we represent features for the digit recognition problem? One possibility is to use human knowledge, right? Okay, for example, human knowledge may tell us that when we write down a digit, there's symmetry that's important for reflecting what the digit is, and there's density. Okay, for example, a 5 is arguably denser than a 1, and a 1 is arguably more symmetric than a 5. Okay, so for each image there, we can do some image processing, okay, and extract those symmetry and density features. For example, to compute the symmetry, we may try to maybe flip the image and subtract the original version and the flipped version and calculate the total sum of the difference and so on. Okay, so once we extract those two features from the images, okay, we can then plot every example that we see on, for example, this is a 2D space, okay, so we can use the 2D space to visualize what happens, and you see that, okay, so basically the blue circles, okay, are ones. Okay, so we see there's a 1 somewhere here, there's a 1 somewhere here, that comes with relatively high symmetry and low density. Okay, and for 5, it's highlighted in red, the red cross here, and you can see that 5 comes relatively lower symmetry and higher density. And of course, there can be noise. Okay, for example, this comes from the original data actually. Okay, if you see, this is a 5. This is a cross, not a 1. Of course, as you can imagine, no sane human being can possibly recognize this as 5 and so on. And this is possibly caused by low quality scanning or whatever, or wrong labeling and so on. Okay. And one good thing about this is that it shows you how noisy real-world learning problem is. Okay, this is a typical real-world learning problem. Okay, while many of the examples may have patterns. Okay, for example, 5 coming us with a lower symmetry and higher density, there will inevitably be some cases that are noisy. Okay, and therefore, how to combat noise is actually an important problem in machine learning that we will discuss later. So that's how we do learning by concrete features. But of course, okay, we may want to do something different. For example, assume that we can represent each of those grayscale images as 16 by 16 pixels. So basically, we then have a long vector. Okay, if we just vectorize the matrix, we have a long vector that's 256 dimensions long, containing the grayscale of each pixel. Well, the combination of those pixels tells us what digit it is. Each individual pixel carries some simple physical meaning. They're still physical meaning, but are arguably much simpler than the concrete features. Okay, but okay, machine needs to kind of aggregate the information within those features in order to get some understanding of what's going on in the recognition process. Okay, so there are other problems with this kind of raw features like image pixels, speech signal, and so on. Okay, many of the signals that you get directly from sensors are raw features, okay, in some sense. Now, this follows some questions you asked last time. Okay, when you get those raw features, raw signals, one way to start doing this is to think about concrete features, to use whatever processing approach you can think about, digital image processing, signal processing, and so on, to try to convert those raw features, raw signals, okay, into something that's more meaningful for the task. That's one approach, okay, and actually that's the traditional approach in many fields. Now, machine learning allows another direction, actually. Okay, we can still use the old one, and the old one actually has a fancy name in machine learning called feature engineering. Okay, feature engineering actually means try to use your human knowledge, okay, to think about what features or what feature combinations to use, okay, for your machine learning task. And after you think about those, try to convert whatever raw feature you have to those more concrete ones for machines to work on. Okay. But there's another way of letting machines convert to concrete ones. Okay, not nowadays, not only humans can do that. Okay, but we also expect the machines, okay, can possibly help convert raw features to concrete ones to assist learning. And this is what people did. And actually, this is part of the convolutional neural network model that we will study much later in this class. So basically, what a machine can do in this kind of model is trying to do some divide and conquer. Okay, from the raw features, okay, that the machine see in the first place, it tries to find little, for example, patches, and detect, okay, whether those patches are in the image or not. Okay, so basically think about there are mini tasks of detecting the patches. And after detecting whether there's a patch or not, okay, now some patches occur more frequently in one of the digits. For example, this underline here appears more frequently in 1, I believe, and this appears more frequently in 5, and so on. So then machines can learn on top of those patches, okay, to, for example, make a classification on whether the digit is a 1 or a 5. And those patches, okay, those steps in converting from the raw feature to patches, okay, is one way for machines to extract more concrete features from raw one. So those patches are more concrete in some sense. And the so-called deep learning is extending this concept for multiple levels. Okay, each level makes the raw feature more and more and more concrete. Okay, until the end where we have very, very concrete features that carries sophisticated physical meanings. Then the machine can work on top of those features to conduct the learning task. Okay. So this is called a layered extraction from simple to complex features, and we will discuss those much later in this class. And it's natural for difficult learning tasks with raw feature, like computer vision or speech recognition that we discussed. Because, as we mentioned, traditionally in those fields, okay, they rely on human-designed features. But now human-designed features have reached arguably their ceilings. Okay, so basically, it's hard to improve them anymore, and therefore, people really want the machines to get extract those patches or whatever patterns, feature patterns from data, so the machines can do a better job. And actually, many of the strong deep learning performance that you see nowadays are success stories of this route. And this is what people do in deep learning. Currently very popular for vision, for speech, basically for fields where you can gather lots of raw data, but you are running out of idea on how to extract meaningful or concrete features from those data. Okay, and another level, okay, even simpler or more abstract than raw features is called the abstract ones. And this is the problem we encountered in KDD Cup 2011. If you recall that in that particular problem, we're building a recommender system where we're given user ID, item ID, and the corresponding rating. And we're predicting the rating that some user will give to some item. You can view it as a regression problem. Okay, rating is a real value that you want to output, and your input space are basically two IDs. Okay, and those IDs are non-negative integers. So you can say, okay, so you have a regression problem. Your input space are just two IDs, and the output is regression. But those IDs are arguably even less meaningful than the pixels that you saw in the images, right? Because, okay, those IDs are sometimes just sequentially assigned by the system and so on. They do not carry any concrete information about the user. They do not carry any concrete information about the item. Actually, no concrete information, very little or almost no raw or physical nor physical information as well. So this is even more difficult for machine learning. Okay. Similarly, they can use the help of deep learning and so on to turn them into more concrete ones before processing. Okay, but we just want to highlight, okay, that it is also an important task that you will encounter in real life. Okay, you won't always get concrete features. You will encounter raw features or abstract features as well. And for abstract features, traditional way of converting them to concrete ones is to do some, for example, use some properties that are statistical in nature. Okay, for example, we don't know from the user ID, we don't know anything. Okay, but we can get the average, okay, rating from the user as a representation of the user ID, then it carries more information. Okay, so some statistics on that particular user or on that particular item can be one way of converting those raw abstract features to concrete ones. And deep learning can be another approach for making the conversion. Okay, so abstract features again need feature conversion, extraction, construction from human or from machines to be really useful for machine learning. And here are the three parts that we described. Concrete, okay, carry physical meaning, arguably easiest for machine learning. Raw and abstract need some processing from machines or humans before they can be useful. And in this class, at least in the very beginning, we will mostly consider easy inputs, okay, where we have concrete features to begin with. And later in this class, we will learn how to do feature engineering, do automated machine construction of features, and so on later. Okay, because this is a leftover, let me summarize the previous lecture first before we get into a Q&A. The previous lecture, we discussed learning with different output spaces, and two most important ones are classification and regression, which we commonly use for many applications and as building blocks of other machine learning solutions. In terms of learning with different data labels, the supervised setting where we have all the labels is arguably the most important one and can be extended to other different settings as well. And there's learning with different protocols, more interactive one like active learning and more sequential one like online learning. But the main tool are mostly in batch learning where we feed the machine with a big batch of data. And in terms of learning with different input spaces, where we discussed today, there's concrete features, raw features, and abstract features. And the core one that machines can work on more easily are called concrete features. Okay, so that's the leftover from the previous class, and soon we will be talking about how possible learning is, or maybe whether learning is impossible, surprisingly impossible in some sense. But before we do that, let's check whether we have questions on Slido first. Questions. Okay, we have hello, hi, good morning, what's up? Okay, so there's a question here saying, so patches mean features extracted from the raw feature, a little parted, perhaps. Okay, good question. Actually, for here, patches mean one kind of the feature extracted from the image features. Okay, so this example that we illustrated is very specific to images, okay, where patches usually refer to small parts of the image, okay, that carries some information about, for example, the particular edge or something. So that's what we mean by patches. And as we will learn later, patches surround the design of convolutional neural network, where the main building block within the convolutional neural network, usually called a filter, actually can be viewed as doing some sort of patch detection throughout the image. And for processing different kind of raw features, there are there can be different approaches, okay, for trying to construct, okay, more sophisticated ones from the raw ones, okay. But we are not going into the details for all of those now, and we illustrate what we do with patches simply because hopefully they are visually more understandable. And yes, patches, for images for the convolutional neural network, we talked about the patches detected are considered as processed features. Okay, so we have raw features that are those pixels. Then after some patch detection with convolutional neural network, you get some higher level features. And if you do it deep, then you may get some even higher level ones and even higher levels ones and so on. So every layer of what's called within deep learning makes the feature more sophisticated. And the output of every layer in the neural network can be considered as processed or distilled or digested features. Okay, great. Okay, there's a question in mentioned. So abstract data are data that are meaningful after conversion. Okay, what we mean by abstract data is that data that are not obviously useful before conversion. Okay, abstract. Okay, meaning we don't have their concrete physical meanings and so on. Okay, so we don't know what they are. We just get an abstract ID there. Hopefully, after you do whatever feature construction after the abstract data, you get some feature vectors that are more meaningful. Okay, the meaning may still be hidden, may not always be human interpretable and so on, but still, okay, they are more directly related to your learning task. So machines can do better with those converted features. But before conversion, those are abstract features or abstract data that you may have on hand that you need to think about what to do before starting to build your machine learning system. Okay, great. Let me see. Okay, we don't have many more questions. Let me switch to what we're going to teach today. Okay, so for today, we're going to enter a very interesting topic called feasibility of learning. And in this topic of feasibility of learning, we're going to talk about whether or when learning is possible. And we will start from a question for you, actually. And what we will do here is I'll illustrate the question first, and then we will take a 10-minute break. During the break, I will set up Slido for you to enter your answers, and then we will start our discussion from there. Okay, so what's our question here? Okay, we want to ask you this learning puzzle. What's this puzzle about? Where we want to test your human learning. So let me illustrate what you need to do in this human learning task. We have 6 pictures, 6 patterns on the top. Okay, and 3 of those patterns are labeled as -1, -1, -1, -1. Okay, much like the cross that we see in the illustration in our previous lecture. And 3 of them are labeled +1, +1, +1, +1. So this is a binary classification problem, okay, where we try to classify every pattern that we see to one of the 2 classes, okay, circle or cross. Okay, circle means one to be +1 and cross one to be -1 according to our usual notation. Now, you are human. You are arguably the smartest creature on earth. Okay, so we want you to do some learning with your brain. I'm feeding you those 6 examples. Each picture, each pattern that you see here is your x. So you have x1, x2, x3, x4, x5, x6. Okay, you have 6 examples. Each example is just a 9-dimensional vector represented by black and white or 0 and 1, for example. Your x1 may equal 0, 1, 1, 1, 0, 1, 0, 1, sorry. Your x1 may equal 0, 1, 1, and 0, 1, 0, 1, 0, 1. Okay, so basically, this may be the 9-dimensional vector that you are considering, or basically just 9 bits, okay, to the computer science terminology. So similarly, I'm giving you 6 examples, each 9-dimensional or each just 9 bits, and their labels, and ask you to solve this supervised learning problem, right? Okay, now you know the terminology. This is a batch supervised learning problem of binary classification, where we have arguably row features, right? Okay, so I'm feeding you this. You are smart. You can try to identify patterns from the row features and the labels and so on. And the question that I'm asking you is, build whatever hypothesis you have in your mind. Then I'm giving you a new example. Okay, so this simulates what we do in real learning, right? After you do the learning with the 6 examples, I feed you a new example and ask you on your prediction. So this G is your brain. After your brain returns a hypothesis, then tell me, okay, whether you would predict this particular example as positive 1 or negative 1. That's the task we're going to consider. Okay, so as promised, we will take a 10-minute break first, because so we can you can actually use the time to think about how to answer the puzzle and so on. And I will open Slido shortly for you to answer your basic for you to input your answers there. Okay, so let's do the 10-minute break. Slido activated. Please enter your answers there. Thank you. Okay, welcome back. It's great to see many of you entered your choices as well as your explanations on Slido. Let's check them first. Okay, let me see. Okay, so first I will okay, I'll need to close the poll here so the results won't keep changing and so on. And let's see how we can view the results. View results. Okay, so here are the results from your poll. Okay, about 52% of you entered +1, 36% entered -1, and the other entered 11% entered the other choice, and so on. Okay, so first thing we see here. Okay, you do not have a very strong consensus, okay, on what the right answer should be. Okay, and that is there's some ambiguity. Okay, so this is a little bit strange because you are all of you, okay, NTU students and so on, are arguably the smartest of this country. And but you cannot reach a consensus, okay, much like the politics we're encountering nowadays, huh? But this also shows you that the answer is perhaps non-trivial. Okay, so this is not something that everyone can immediately agree on. Although more of you gave the answer of being positive and so on, the confidence, okay, may not be that high. Okay, so from those answers, let's check, okay, whether some of you have provided some explanations, okay, on Slido, and you can vote. You can also vote for the explanations that you like the most. Okay, so there's one explanation about +1 saying symmetry. Okay, basically, the argument is that the 3 patterns below are symmetric. And the pattern we provide as the test example is also symmetric, and therefore it should be positive, while the top 3 patterns are not symmetric, and therefore the classification rule that has been extracted is symmetry or not. And if you recall, actually we used symmetry when we try to extract concrete features for the digit prediction problem. So symmetry is definitely something that we human beings believe to be reasonable when trying to analyze the problem. Okay, great. So we have quite some votes for symmetry, while, okay, there's another answer here based on the upper left pixel. When the upper left pixel is black, then the label seems to be -1. When the upper left pixel is white, then the label seems to be +1. And on the test example, the upper left is black, and therefore it should be -1. Good answer. Okay, so we have basically convincing arguments from both sides. And there's another one saying there's no definite answer. It all depends on what feature we choose. I want to highlight here that maybe it's not just what feature you choose, because eventually the feature is being used for classification. Okay, you are not just using the feature, you are building a classifier, a hypothesis G on top of those features. Okay, so therefore, extracting the symmetry feature or one of the pixels as a feature is one thing. Okay, using that particular feature into your classification rule is another thing. So there's a difference in feature, and most importantly, there's a difference in hypothesis. And different hypotheses seems to reach a different conclusion on what the label should be. And the tricky thing is which one is correct, right? Okay, there are two hypotheses, two very convincing hypotheses. Okay, up to now we have symmetry and we have the top left pixel, and both very valid hypotheses, and both getting 100% accuracy on the examples that we have seen, but give very different answer on the test example. Which one should we believe? Okay, and there are other choices. For example, one class member says if the slope is positive, okay, then it should be positive. If the slope is negative, then it should be negative. Although I'm a little bit unsure how to measure the slope here in those images, okay, the slope is definitely also something to think about. Okay, so if you consider those pixels as your observed point or something, slope is basically one way to summarize where the black shows up in the image with respect to the horizontal and vertical axis. Okay, so I'm not sure if the slope argument is correct, but yeah, slope is something you can think about when analyzing the image. Okay. Now, the comment here says we cannot know what fx exactly is, but we can guess a g of x similar to fx. And that's actually the issue that I want to highlight here. We don't know what f is. You can guess. You can always guess. Okay, so basically, and we see that at least many of you have very different guesses. Okay, some of you guess g of x to be positive 1. Some of you guess about g of x to be negative 1. And you don't know f. And therefore, one of you must be wrong. If I say f is positive 1, then the side on negative 1 must be wrong. And if I say f is negative 1, the side on positive 1 must be wrong. Discrete choices, you must answer 1. And therefore, whatever you do, around half of the class would say you are wrong. Okay? Again, much like what we're facing in politics, huh? Okay, and I'm hoping that some of you see the tricks here as this student answered. Actually, let me let me archive those. Okay, for those that we have discussed, so we won't need to keep reading them again. Okay, there's one that's bubbling up. If the top left and center right are black, top left, center right are black is 1. Else it's 1. No, actually it should be negative 1. Okay, if you think about it. Otherwise it's positive 1. But maybe it has some relationship between this pattern 1 to 6. Okay, I don't know. Okay, but again, looking at 2 pixels instead of 1 may be a valid rule as well. Okay, on whether we are saying negative 1 or positive 1. I don't know whether it's related to 1, 1 to 6, but you never know. Okay, maybe there's a hidden variable there that's related. Maybe calculating whether the center of gravity falls on the black block. If yes, positive 1. If not, negative 1. Okay, again, I don't know what you mean by center of gravity here, but I'm guessing some sort of density estimation. And if you look at the densest area of black, okay, maybe you can get some patterns there. Yeah, that's also one possible argument on deciding whether it's a positive 1 or negative 1. Okay, so we had solutions of 1 bit and 2 bits. Now we have 4 bits. Top right, the center, and the right. Okay, actually, I'm not fully sure which 4. The top Okay, top meaning central top, I guess. Top, okay, top right. Blah blah blah. Okay, anyway, so sorry, I cannot follow it in real time. Okay, but basically now now we're looking at 4 bits instead of 1 bit or 2 bits. Now, the question you can think about is this rule better than the 1 bit one or the 2 bit one or the symmetry one? Better or not? Okay, so basically those are hard questions. We can construct arbitrary functions that classify the examples as positive one or negative one, but I'm trying to ask you which one is more convincing to you. Okay. Now, when you solve this problem, you may have your own hypothesis in mind, but now you have read the hypothesis from many of your classmates. What you can think about is really whether theirs are more reasonable than yours or not. Okay, inner product of 2 of these puzzles. Okay, inner product. Okay, that's something. So maybe, okay, maybe you can get a weight vector where a weight vector can also be represented as a pattern, and then multiply do an inner product between that weight vector and the patterns to do classification. Actually, this was exactly what you did in perceptron learning algorithm. You can definitely run your perceptron learning algorithm on this data and get a W and then use it as your G to classify the underlying one. And of course, okay, so now you have another choice for the hypothesis generated by the perceptron learning algorithm. Is it really better than your human constructed hypothesis? Is it better than the 1 bit, the 2 bits, the 4 bits, or the symmetry, or whatever density slope ones that we have thought about? Okay, pixel as positive one and negative one based on existing data, and then calculate the average, okay, to decide. Okay, yeah, that's also something, and that's another way of constructing a linear classifier. Okay, so basically by having every pixel having a tendency of putting for positive or negative and calculating a score for decision. That's building a perceptron. Of course, you can use humans to build this perceptron. You can use machines, perceptron learning algorithm to build the perceptron. Asymmetry we talked about, there's -1 by intuition, and yes, and then you can think about how we human beings come up with intuitions. Okay, if considering the first row, it will be -1 by observation, and okay, the first row, or actually the first the top left bits are similar to the top left bits, but if you talk about the first row, we're basically talking about 3 bits. Okay, that's good. And is X6 symmetric? And yes, it depends on the definition of symmetry, right? Okay, so you can say it's symmetric, you can say it's not symmetric, depending on which axis you are choosing. There are probably hundreds of answers and guesses. Yes, yes, there may be, but we're only getting a handful here now. So yeah, challenge yourself to be a little bit more creative. But I think I convinced you that there's no, possibly no correct answer for this problem, but you can have multiple answers, multiple explanations. There are, okay, the 4 corner, so basically checking 4 corner bits, okay, rather than some other bits that people suggested. Adding pixels if it exceeds or equals to 2, yeah, okay. So now, bottom line, you have lots of great creative answers and so on. And actually, I'm not too sure if we heard explanations from the people who chose other here. Okay, do you choose other simply because you believe there are multiple solutions, or do you choose other simply because you believe that we can output something different? For example, 1126, or 0, or 5566, or whatever. Yeah. Maybe, okay, I told you that this is binary classification, so you may be confined by what I say and say, okay, you need to output +1 or -1. But who knows? Okay, maybe you can output a soft answer. Okay, this is 52% +1 and 48% -1 or something like that. But anyway, this is the challenge that we face in machine learning. Okay, and we have discussed all this. I actually listed a bunch of reasons here in my slide, okay, and the discussion went on. I didn't write it down, but you can always check Slido or our YouTube video back for whatever we discussed. But here are some reasons. Some are arguably simpler to describe. Others are at least look much more challenging, more sophisticated. But all seem to be valid reasons, okay? All the reasons here and the reasons that you have described on Slido. Now, if I am the adversarial teacher, actually it's not if, I am the adversarial teacher. Okay? Whatever answer you give, for example, you say, I believe this is +1 because, okay, of the symmetry argument and so on. I say, you are wrong. My intention, the f of x in my mind is to inspect the top left corner. And if that corner is black, you should return -1. Otherwise, you should return +1. How can you possibly think about symmetry? No, you must be wrong. This is the adversarial teacher, not the encouraging one. The encouraging one would say, oh, yes, okay, everything you say is right. You are very good argument, very creative, and so on. But for adversarial teacher, she or he can always call you wrong. Or on the other side, if you say, yeah, I believe it's -1 because blah, 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 the adversarial teacher can always say, you are wrong because, okay, in my mind, I am having a target function that's evaluating the symmetry. Come on, you're smart. How can you not observe the symmetry? That's so obvious. So you are wrong. Whatever you do, your adversarial teacher can always call you didn't learn. I can always give you a 0. Yeah. Okay, maybe not yeah for you, but think about that. Okay, if this kind of arbitrary thing can happen, if there's no standard answer for measuring the correctness and so on, if the teacher has lots of freedom to modify the answer after hearing yours, for example, then you are always wrong, or the teacher can always call you wrong. That's something that seems to make learning doomed, because for learning, we want to learn something outside. Okay, but if the outside judge is unfair in some way, or if we don't have any restrictions that govern the outside judge, okay, then whatever you predict, really, you can be called wrong. No learning is possible. Or think about this. This is a brainstorming problem that I saw a few years ago. Actually, not a few years ago, 10 years ago, when I started teaching machine learning. And this says, okay, the top 2% smartest people of the world can solve this problem. Okay, only the top 2%. So test yourself whether you are the top 2%. This particular problem can be viewed as a learning problem, saying, okay, if I tell you that there's a rule that converts 532, this particular vector, into a number 151022. That's the particular rule. Okay? Then what should this vector 725 be converted to? That's a problem. So you have one example, one input vector, one desired output. Of course, it's real valued in some sense, or integer valued, and you can call it a regression. And then try to learn a hypothesis to predict on this new example and tell us what your answer is. Okay, you can input your answer on Slido, but because of the time constraints, we cannot let you play every game here, but I'll show you the answer that I thought about in the very first place. The answer I thought about is this: 151026. How do I come with that answer? Well, I find that this 532, it sums to 10, and therefore if I let 151012, I don't know, maybe it's someone's magic number, sum with those 3 digits, then I get this number. So to get the corresponding number here, all I need to do is sum up these 3, which give me 14, and then sum with 151012, that's 151026. See how smart I am? Okay, I got a formula immediately after learning from this one example. This particular formula is a linear formula, okay, much like the perceptron we have used in some sense without the classification, and then I can get a number that sounds reasonable. As you can see, this is not the desired number of this brainstorming problem. Okay, the particular answer that was provided by the organizer is this: okay, 143547. And the argument is that if you check the first 2 digits, multiply them, you get the 15 here. So if you check the first 2 digits, multiply them, you get the 14. So first 2 digits comes from the first 2 numbers of the vector. And then if you check the digits 5 and 2, you get the 10. So check 7 and 5, you get 35. Okay, and the third one is a little bit tricky. Okay, so basically it says if you check 15, change the color, 1510, and then sum them and then deduct it with this 3, you get the 22, which are the last 2 digits. Okay, so we can do the same here. We have 14 plus 35 minus 2. That's 12 and 35. That's 47. So we get the 47. That's the desired answer. That's the claim to be top 2% answer. While I don't know whether I belong to the top 2% of the world or not, I believe my answer is equally valid. So again, another example to show that we can be creative, okay? Creative, but it is a little bit tricky on how to justify that our creativity means we learned something. Okay, we can say we learned something. Okay, we learned a really sophisticated underlying rule and so on. But for here, we learned something too. Okay, maybe not as sophisticated, but equally reasonable and interesting. Okay. Another fun before we continue. 1415. Okay, consider this to be a sequence. Okay. So in many of our previous mathematical education, we say that we should observe patterns in a sequence. So if you get 1, 2, 3, 4, you would expect the next one to be 5, the next one to be 6, and so on. If you get 1, 2, 4, 8, you get the next one to be 16, 32, and things. Okay. If you get 1, 1, 2, 3, 5, 8, and so on, you know it's a Fibonacci sequence. Okay, so sequence prediction is arguably a very intelligent behavior that's related to machine learning. So again, I'm giving you 4 numbers as the first 4 values of the sequence. Now I want you to predict what the next number is. And what I'm going to do here is to turn on Slido. I should be able to do it with 1 click. Let's see. Okay, I'm turning on another Slido poll for this. Okay, what's the next number in this time series or in this sequence? Okay, so now please input your answer here. Okay, what's the next number? 1415. What's the next number? And we will wait for you for 2 or 3 minutes, okay, before when I organize some Slido questions and so on, then we will continue our discussion. Okay, so as I clean up the questions here, please input your answer on Slido. Okay. Okay, when you answer the question at the same time, I can say, okay, so when the assumption of the problem, there's one question here. When the assumption of the problem here has only -1 and +1, how do we come up with the third solution? Yeah, that's good. So I was kind of tricking you, okay, that I gave you an assumption or a restriction on the output, but telling you whether you can think of the box for the third solution. But also think about it. Okay, in life, okay, if you train an actual machine learning agent, okay, in life, do you want the machine learning agent to think out of the box for the third solution or not? Sometimes yes, sometimes no, right? Okay, if you believe that machines should be creative or be even more creative than humans, then maybe you should allow the option. On the other hand, if you are worried that the machines would get out of control like Skynet or something, then maybe you should not, okay, give the machine the third option. So it's a very interesting philosophical question on whether you should provide an answer out of the box when you are restricted for the 2 output case. Okay, so that's something we should all think about. Okay, and there's one comment here on n must be large enough. Okay, so that's an interesting argument, okay? And we can encounter them later, but one thing we can think about is how large is large enough? Okay, for example, for this sequence prediction, I should give you some initial values of the sequence. How large is large enough? If I give you 4 numbers, is it large enough? If I give you 10, is it large enough? If I give you 1126, is it large enough? Okay. True, we can think that in the previous example where we only have one case, maybe n is not large enough. But think about the pattern case. Even if you get arguably many more examples, it is not always obvious on whether we're doing correct or not. Or what we're trying to convince you is really, regardless of how large n is, okay, we may not be able to claim learning if we don't make other assumptions. And we will encounter that a little bit later. Okay. Yeah, so okay, I see that people are filling in some answers in Q&A. We won't get into many details here, but I do like to see the poll's results. Let me stop the poll here. And the results are dun, 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 dun. Okay, so many of you entered 1, and a few of you got 0 or 3 or 5. Many of you are attracted by the mysterious number 1126, and there are other. For example, if you think of those as the digits of pi under the decimal points, okay, then 1415. 926 is the digits of pi and so on. So the next maybe 9 or something. And let's look at some of the answers that I provided. Okay, for example, if you're looking for a pattern, it can be 0. Okay, by subtracting two previous digits, okay, that are 2 steps and 4 steps before the number. And it can be 1, okay, as many of you chose. Okay, that's the pattern of 1 4 1 5 1 6 1 7. It can be 2 by doing something Fibonacci sequence like, okay, but with values 2 steps and 4 steps before. And if you want, you can easily get the next number to be 3, the next number to be 4, to be 5, to be 6, and actually to be 116 as well. Any number can be the next number. So again, lesson learned. If any number can be the next number, then an adversarial teacher can always call you wrong. Right? Whatever number you answer, I can always say, ha ha ha, you are wrong, because that's whatever the pattern I have in mind. Okay, so you see, we have an F there. Okay, that's in the teacher's mind. Okay, the teacher teaches you through some examples, and you guess the next one. That seems to be the natural machine learning setup that we have discussed for 2 weeks now. But now I'm challenging you that this setup does not allow you to learn. At least that does not allow you to learn, always learn correctly, or does not even allow you to learn almost always correctly. Because, okay, in every scenario you face, the worst case situation is that you will be called wrong, because you can have a very different G compared with the adversarial F that your teacher may have in mind. That's the problem. And if those are not enough to convince you, let me add to a more reasonable learning scenario. Now, instead of 9 bits, okay, in the first example that we encountered, let me consider just 3 bits only in our input space. 3 bits, okay, no more, no less. So for 3 bits, you do know that there are only 8 patterns. Okay, and then for those 3 bits, assume that we know the correct answer corresponding to those 3 bits. Okay, so we have circle, cross, cross, circle, cross. Okay, so basically, for those 3 bits, assume we have gathered 5 examples. So what we do is we have 5 out of 8 examples. Come on, we only have 8 examples in the world. We now gather 5, but 5 is majority, right? Okay, we get more than half of the available examples and so on. Okay, so we ask the machine to learn from this data set. Learn from this data set. Okay, so we have examples that's x1, x2, x3. We have their labels and so on. Throw this to your perceptual learning algorithm or whatever learning algorithm you're interested in. Okay, get a hypothesis and let's evaluate the hypothesis. Even better, why do we restrict ourselves to all the perceptrons? We can actually, because this is a discrete function, we can actually enumerate all the possible f. Okay, and then use all those possible f as our hypothesis. We only have 8 examples, and the outcome on those 8 examples are either positive or negative. So we only have, for this all, 2 to the 8, which is 256 possible functions. Add them all in, okay? Put all those functions as our candidates. We must be able to find a good hypothesis, right? Okay, let's do it. So let's pick a G from H with all that is correct on all of the 5 examples we have seen. Now the question is G similar to F or not? Okay, so let's see. Which G do you want to pick? I say, okay, I like even numbers. So let me have this guy as my G. Okay, so having this guy as my G actually means this G predicts circle, circle, cross. Okay, let's say I have a very smart machine learning algorithm that picks this guy as my G. Okay, this G is good. And is this G good inside D, inside my data set of the 5 examples? Yes, this G is perfect. It has circle, cross, cross, circle, cross. Very perfect. But is G good outside D? Let's see. G is good outside D if this is the true F. Right? That's a big if, because all those 5 hypotheses seems to be possible F. Okay, they seem to be equally possible in some sense. And therefore, this guy is also a possible F as well. What happens if this F7 is the underlying F in your teacher's mind? You pick F2 as your G, then you are totally wrong. Okay, so basically you see in all the candidate F, okay, there's something that makes your G perfect, there's something that makes your G very wrong. Therefore, we cannot guarantee anything about whether G equals F outside D, because we don't know which of them is in the teacher's mind. There's the best case where we are perfect. There's the worst case where we are very, very, very wrong. And of course, there are intermediate cases as well. So from this, you see that with enumeration, even when we have a data set that's sufficiently big, 5 out of 8 is sufficiently big. We still cannot guarantee, and even if we fit the dataset on hand perfectly, we still cannot guarantee anything outside F. We can jump from the very good hypothesis to a very bad one if we have an adversarial teacher or anything. Or on average, if I do an averaging over all those cases, really we did not learn. Okay, we are doing as good as or as bad as a random coin flip. So learning from D to infer something outside D is doomed if any unknown F can happen. Okay, that's the message we try to convey through all those brainstorming examples and now more formally in the learning scenario. This is the learning scenario phase. We throw into a hypothesis, we have a data set that's of sufficient size. We try to get a G that matches the data on hand, and we try to predict outside of the data. And when we predict outside of data, we see that the best case and the worst case averages out, and we cannot learn if we don't make any further assumptions on the problem. Technically, this is called the no free lunch theorem for machine learning. We won't get into the details of proving that, but I want to convey the philosophical thought here. The philosophical thought is that if we don't have any assumptions on the learning problem, for example, if we allow anything to happen outside we allow the adversarial teacher to pick any target function, okay, that's sure he has in mind, then all learning algorithm performs the same as a random coin flip, essentially. Okay, so basically, you will have the better cases that your learning algorithm succeeds. There will be a matching worst case that your learning algorithm failed significantly if you don't make any assumptions. If you have assumptions, of course, your learning algorithm would do well when things match your assumption, and your learning algorithm may do worse when things do not match your learning assumption. That's fine. Okay. So the argument here is that we need some assumptions for the machine to proceed, and no algorithm is best for all the learning problems. That's very important to know in this very beginning of the machine learning class. Okay, you are not here to learn a learning model that's the best for all kinds of problems that you consider. No, every learning model has its assumptions behind, and it has its cons and pros, has its advantages and disadvantages. If you face a scenario that matches its advantages, then your algorithm can do well. Otherwise, it can fail too. There's no universal algorithm that does best on everything. Okay, this is much like the human society, right? You won't be good in every subject that you learn. You can do better on some subjects. You can do worse on some subjects. It's totally fine. Okay, as long as you know what your strong subjects are and try to prioritize more on them, you can do well. Similarly, you should think the same for your learning algorithm. In this class, you will learn, or we will try to teach you the cons and pros of every learning algorithm and their design philosophy or assumptions behind. Then, using those knowledge, hopefully you will choose your learning algorithm more wisely when encounter real-world problems. That's what we want to do. Okay, questions. Let me check the Slido here. Okay, for those number guessing, I'll just I'll just archive those. Okay, thank you for the active discussion there. How to prove the next number is 1126? Actually, I can answer this one. Okay, so some of you may know something called interpolation. Okay, and interpolation basically says you try to use, for example, a polynomial or something to do some fitting. Okay, so what you can do to prove the next number to be 1126 is really to set up an interpolation problem. Okay, like you want to interpolate 2D points 1, 1, 1, 4, 2, 4, 3, 1, 4, 5, and 5, 1126. Okay, and set up that interpolation problem. You will get a curve that can serve for your prediction. Okay, and okay, there's color 1, 1126, 9. Yeah, there are things like that. Okay, and depends on the algorithm. Are these different answers just because that we have too few conditions? Okay, I like this way of saying this. Just like one solves a higher order system with insufficient condition. Put it in another way. Okay, condition is what we will talk about in terms of assumption. Okay, so basically we will need to have some assumptions, some restrictions, okay, or some conditions, as you name it, to make learning successful. Currently, we seem to be set up our learning problem to be too wild in some sense. Okay, we are allowing any hypothesis. We are not making assumptions about the connection between training and what's left and so on. Okay, so basically the assumptions that we will talk about can be viewed as conditions in some sense. Okay, in the next part. And are we talking about overfitting? Not yet. Overfitting is an important topic in machine learning, and we will discuss more about that later in the lecture. But here we're not yet talking about overfitting, okay? Meaning we are just talking about the infeasibility or impossibility of learning if we don't put any assumptions, okay, or if we just want magic. Okay, machine learning is not magic. Okay? You build machine learning models on top of the assumptions that you made and derive reasonable result and observe reasonable algorithmic behavior and so on. And yes, even after we carefully design, we can encounter overfitting, which will be discussed later. But for now, we're not talking about overfitting yet. We're talking about really trying to not make any assumption at all. Okay, much like what the no free lunch theory says. Try to not pay for your lunch, but want to eat something. This is just not possible. Similarly, if you don't make assumptions on your machine learning algorithm and want it to do well, in some cases, it is not possible. A machine learning algorithm can do better here, but do worse there. Okay, and on average, it's not really better than any other algorithm. Okay, great. So let's switch back to the next part. Now, let's see how we can infer something unknown under assumptions. Okay, so now we know we need to have assumptions. Let's say our goal is to infer something unknown, infer the target function that we don't know. Have we encountered a scenario where we can infer something unknown when we have assumptions about what happened? Okay, so the motivating example that we will use is the so-called bin model here. You consider we have a bin, a jar in some sense, okay, and you are trying to evaluate, okay, how many orange marbles there are in the bin. So in the bin, assume there are many orange and green marbles. Okay, and from those marbles, you do know there's a portion of the marbles being orange. Okay. Do we know the orange portion? We don't know unless you count one by one, right? You can pick, really take out the marbles and count, okay, the number of orange marbles, number of green marbles, one by one, and you get value. We will consider the marble to be so big that we cannot do the counting. But still, we want to know the portion, okay, the ratio of orange marbles within the bin, within the jar. Do we know for sure? No. But what can we do in order to get an estimate, okay, or to get an inference, okay, on what the possible value is? Well, as you can imagine, what we can do is to do some sampling. Okay, this is what you typically learn in your statistics class. Okay, so imagine that you go into the bin and randomly, okay, of course, assuming uniformly randomly, pick up some marbles. Okay, and this process is called sampling in statistics. And what happens if you pick up 10 marbles and got 3 of them to be orange? Well, you still don't know what's the actual orange portion within the bin is. Okay, we will call that orange portion or orange probability to be mu. Okay, mu, mu, mu. Okay, and this mu is unknown to us within the bin. But after you do the sampling, let's say you sample 10 marbles, okay, and 3 of them are orange. You do get an orange fraction. That's 3 over 10 here. And the 3 over 10 is now known to you. So you, in terms of statistics or sampling, you typically use this 3 over 10 to be an estimate, okay, to be an inference of the orange probability, the mu within the bin. So we use nu, to estimate mu, mu. Okay, so basically that's what happens during sampling. Now in sampling, we made some assumptions, right? I put a big assume here, okay? Assume we sampled n marbles independently. That's an assumption, okay? That's actually very important in order for this inference to work, okay? If I don't make the assumption that things are being sampled independently, then, for example, I can look at the jar. I like orange so much, so I only pick orange jars. I don't sample them independently, I just pick the orange. And then I say, ha, you see, the whole bin is orange. No, this is not a valid inference, right? So by making the assumption that we're sampling uniformly, we get the power of doing some inference. Maybe not perfect, but we at least better than knowing nothing. So what does this inference say? This inference says, okay, First, we still don't know, okay, whether what's the exact number, what the exact orange probability is. We don't know for sure. Okay, it's not 3/10. Okay, it can be any number. It's most likely near 3/10, but we don't know. Okay, it can be 0.29999. It can also be 0.35 something, or maybe if you are not lucky, it can be 0.8. Okay, but it so happens that you only get 3 orange marbles out of 10. We don't know for sure. But, okay, it tells us that if you are lucky enough, then this in-sample value, okay, this value that we can evaluate on our hand is likely to be close to the unknown value that we're interested in. Okay, so this is called nu is close to mu. Formally, what does this say? Mathematically, it says, okay, through this sampling process, the probability that these two values are far away, and this far away is evaluated by a given parameter epsilon. The probability that the two values are far away is bounded by an exponentially decreasing term, which is exponentially decreasing with respect to the number of samples, the number of examples that you have. So if you sample 10, okay, you have a bound. If you sample 100, 1,000, then you get a bound that basically tells you the probability of the two values being far away is really, really, really small. Okay, for example, think about it. Okay, if you have a bin, if you have orange probability being 0.2, and you sample 10,000 examples, okay, then most likely you will get around 2,000 examples in terms of 2,000 examples or marbles to be orange. Around 2,000, not exactly 2,000. You can get 1,997 or something. Okay, but basically you know it's going to be close by. So this is the probability. Of course, sometimes you're unlucky. Okay, even if the orange probability is 0.2, you pick every time independently, you get orange. It is highly unlikely, but possible, right? The probability of getting an orange every time after 100 times is 0.2 to the 100th power, which is really small. But it can still happen if you are totally lucky. And this is called Hoffman's inequality. Okay, we use that inequality implicitly in our real life for marbles, for flipping a coin, for polling, right? Okay, so basically when you use phone polling to know the support rate of some candidate or something, you are basically doing this. Okay, assuming you are sampling from your underlying universe in some way, then the sample that you get can tell you something with a high probability about the underlying number. Or in math terminology, we call this statement nu is close to mu, okay, or nu is equal to mu, as probably approximately correct. Approximately because they are epsilon apart, right? Not exactly, but approximately. And probably because there's still a really small chance that things can go wrong, but really small. Okay, with a high probability things would go right. You can claim that whatever estimate you get in terms of nu is close to the mu that you are actually interested in. You don't know it, but you are interested in that. That's Hoffman inequality. It's valid for any number of samples, any tolerance in terms of approximation. It does not depend on mu, and therefore we do not need mu to derive those bounds. Or it basically this bound works for every mu that you're interested in. And when we get larger sample size or looser gap, then there's a higher probability that we can claim this equality or similarity, or we can claim this inference to work. So if there's a large number of examples, we can probably infer the unknown value by the known value under the IID sampling assumption. And that's the tool we're going to use. The next we're going to do is to connect this with the learning scenario. Now we're only in the bin or coin flipping scenario, saying, okay, if you have an unknown value, but you are allowed to make assumptions on how you can get observations from this unknown value, then we can infer something. Now we're going to use this for the learning scenario where the unknown thing is f of x or f, right? The unknown function is f, and what we want to infer is g or h. Okay, the hypothesis in the hypothesis set, or actually the best hypothesis we can get from the hypothesis set. Okay, so that's are the next two topics. But for now, we see that by making assumptions, we step out. Okay, we can do something to infer the unknown values. Okay, questions. How do we come up with an ideal assumption? Is it anything to do with the domain knowledge? Okay, that's a very good question. For domain knowledge is a good starting point to make the assumption. And for some of the assumptions, they are there for mathematical purposes. For example, the IID assumption is there for mathematical purposes. Almost always, okay, the real world problem do not come do not come with data that are IID sampled, but having IID assumption allows us to do something to design a learning algorithm and worry about the non-IID nature of real-world data later with other amendments and so on. Okay, and in the real world, usually we try to understand the problem on hand with domain knowledge or data analysis or whatever before we make assumptions about how to do the modeling. What does epsilon mean? Okay, epsilon captures the possibility that what you observe may be different from the actual value. For example, if the actual underlying value is 0.2, your observation after gathering, let's say, 100 examples, maybe you have 23 marbles being orange. So 23 divided by 100 is 0.23, which is different from 0.2, but close enough. So epsilon actually means what we believe to be close enough. Okay, and it's an essential construction in this Hoffman inequality. By the way, we're not going to prove the Hoffman's inequality in this class simply because we view it as the background you can develop in your other classes and so on. Okay, but for those who are interested in, the proof is actually a very good way to test your mathematical understanding in probability and statistics. Does IID mean independent sampling? It means independent and identically distributed. Okay, so there are two I's. Independent, identically distributed means we're sampling from the same distribution. Okay, in terms of the coin example, for instance, you're flipping the same coin, or in terms of the bin, you are trying to get marbles from the same bin, and therefore, in some sense, okay, the same distribution. Wondering why the inequality is written as the difference being greater than epsilon rather than less than epsilon. Yes, you can actually write the inequality in another way. Okay, and the current form tries to highlight that the probability that something bad happens. Something bad happens, meaning you have a sample on hand, the sample is very different from what's in the bin. That's bad, right? Because we're doing estimation. What's good is that we can use whatever is on hand to estimate whatever is in the bin. But if we get a sample, but the sample is totally not representative of whatever is in the bin, that's bad. Okay, so the bound that you see tries to bound the bad probability. We're trying to argue that the bad probability is small. Okay, think about the bad thing. Okay, for example, if we're using polling to predict who will win the next election or not, and then when you do the phone polling or something, you get into a group that may not give you the true answer, or maybe you sample a group that is not representative of the distribution of all the voters and so on, then you get wrong conclusions. So that's bad. And the bound you see tries to say the bad probability is small, and therefore, if you're not overly worried about your luck, then you should try to trust that your inference is valid. Okay. And there's a question in Mandarin. When n is big, is the upper bound big? And well, that's move us close to the correct probability. Actually, if you look at the bound is here on the top. Okay, when n is big, this guy is exponentially decreasing. So the upper bound is small. It's close to zero. It means hardly any bad event would happen. Okay, really. Okay, so you should trust yourself to be lucky. And when no bad event happens, you can say that mu and nu are really close to each other, and our inference is most of the time okay, correct. That's what this bound says. When n is large, bad probability is small. When bad probability is small, the two numbers are close to each other. So what we know, the nu is a good inference of mu, what we don't know. Okay, great. We answered all the questions here. Now let's take a 10-minute break before we continue. Thank you. Okay, welcome back. As many of you have seen, I have announced a poll on Slido, which will be used later in the class, but you can try to run the experiment first. Okay, so basically it asks you to find a coin and flip it 5 times and tell us the number of heads that you get. Okay, we will discuss what it means later for that part. But for now, let's try to connect what we have learned in the BIM model to actual learning. In the BIM model, we have something unknown, the orange probability mu. And we try to select marbles from the bin where there are 2 kinds of marbles, orange or green. And we sample and examples from the bin by an IID process. Okay, so basically keeping this identical, and this allows us to use Hoffman inequality to connect what the portion of orange that we observe, okay, which is the mu here, to the mu that we're interested in. So that's the BIM model. And what do we do in learning? In learning, what we don't know is the target function. Okay, the target function, that's something that we really want to know, but we don't know. Now, how do we express the target function to be something closer to the BIM model that we have seen there? Well, let's first look at a value, because the function is just too hard to control and so on. And let's first look at a function evaluated on some values, okay, some inputs. And what we're interested in is really to know whether our hypothesis is the same as the target function or not. Okay, we're not interested in the prediction of the hypothesis. We're interested in evaluating the difference between the prediction and the ideal value. Okay, so the prediction can be positive, it can be negative, for example, for binary classification, but we want to know whether it's correct or incorrect. Okay, that's what we're going to do here. Okay, we are going to translate, okay, our goal of evaluating H, of knowing whether H is good or not, to evaluating H on each example, on each X, okay, and see if it's correct or not. Each example will be viewed as a marble in the bin. Okay, that's what we're going to evaluate. And if the hypothesis is wrong, we color the marble or the example as orange. If the hypothesis is right, we color as green. So the orange probability, the orange portion, is how much H is wrong. Okay, so the total number, the total portion of orange cases means how much H is wrong. And we check H on a bunch of data sets that are IID samples. So think of this big X, okay, as the bin that we're considering. I should use gray here. This big X as the bin we're considering. Now, if we have a hypothesis in mind, hypothetically, okay, or imaginarily, you can label every example in your space with either orange or green. I have a hypothesis, okay, and now comes every example in your space, you can color it as orange or green. Now, this is imaginary. I'm not asking you to actually color every example in your space, right? But what you can do is sample some examples from that space. As long as we assume that these examples we sampled are IID, then the performance of the hypothesis on those examples are just like the samples that we get from the marbles. Okay, so that's the basic idea. What we can assume what we observe comes from an IID process that's colored by the imaginary process that we have considered. Then by evaluating the colors of marbles that we have on hand, we can infer the unknown quantity, which is how often H is different from F across all examples, all possible X. And so that's the basic idea of making the connection, or we're reducing the learning problem to the bin problem here. Now, of course, I need a little bit fixing here. For example, in the marble case, when we talk about sampling, we sample IID and we do some sort of uniform sampling across X, across marbles. Right, we assume that every marble has its probability of being selected and it's roughly uniform and so on. Now, when we're doing learning, okay, most likely, okay, we will have different probability on different X. Okay, for example, if you are getting images from the real world, then some images may appear more often than others. So in terms of sampling, okay, there's an underlying probability on those X. Okay, that's P of X, which is likely not uniform. Okay, kind of a little bit different from the marble case. Luckily, Hoffman works, okay, as long as we're doing IID sampling from the same P. Okay, IID means identical distribution, and the identical distribution now we're considering is P, regardless of whether P is uniform, like the marble case, or non-uniform, like the typical learning case. It doesn't matter. Okay, we sample, okay, and then the estimate, in-sample estimate, okay, the marbles that we have on hand are basically, in the learning terminology, the performance that we can observe on the data set can serve as a measure, as an estimate, or as an inference to the unknown number that we want to get. The unknown number is what? How much H is wrong with respect to P. How often H is wrong with respect to P. If P is if some X is more frequently sampled, okay, then if it's wrong, it counts more. Basically, we're kind of trying to estimate the error rate of the hypothesis with respect to P. And by our construction here, the error rates, okay, the unknown probability that we want to estimate can be inferred by the norm fraction. And the norm fraction can be just computed with what we have on hand, the data sets that we have on hand. So basically, this is what we do to use the Hoffman inequality. If we have a large number of examples and IID examples, much like what we're doing sampling with the marbles and so on, we can probably infer the error rates of the hypothesis by the norm fraction. So this is the new flow, okay, that we have here. We now need to assume an unknown distribution and do sampling from that distribution. We'll assume our data is sampled from the distribution. Otherwise, okay, we will fall into the trap that's no assumption, no learning. Okay, now we have assumption. Assumption is our data comes ID from the distribution, and we use the same distribution to do evaluation, to sample new test data to do evaluation. And what we're interested in is to know whether this one hypothesis is similar to F or not. So there are two values that we're interested in. One is usually called E in, which measures whether the hypothesis is the same as the label that we have on hand. So this is the sampled result from the bin in some sense. And the other is called E out. So basically how the hypothesis perform with respect to all possible examples that you can get from the probability. Here I'm using this E here to mean expectation. Okay, if you have trouble understanding the expectation here, just think of the term as error rate. So how often your hypothesis would make an error. It's much like how often you would encounter an orange marble. So we have something known, that's E in, our in sample error, what we have on hand. And what we want to estimate is E out, the error rate, the out of sample error, the general test error. You'll notice that I put here a different flow, okay, some different arrows here and there other than the G. This is because currently what we're assuming is one fixed hypothesis. We're not assuming multiple hypotheses like a hypothesis set and everything. We just say, okay, we have a fixed hypothesis. Let's see how things go. So we will amend this later when we talk about multiple hypotheses and learning algorithms and so on. But for now, let's keep things on another route. Okay, saying what we have learned so far with the BIM model allows us to know whether H is similar to F as long as we assume an unknown distribution that generates the data we have on hand and that generates how we're going to test our system. And then things are just rewriting the Hoffman's inequality. Now this E in replaces the nu, which is our in-sample error in the BIM case. This E out replaces the mu, okay, which is the number we're interested in. Others are just Hoffman inequality. And same as the BIM analogy, it's valid for all number of examples, all tolerance thresholds. We don't need to know E out, and therefore both F and P, which are related to calculating E out, can remain unknown. And then by using Hoffman's inequality, we can say E in is probably approximately close to E out, okay, where probably comes from this low probability thing, and approximately comes from this F shown here that we won't be exact, but we will be close by. Okay, now let's see how this affects learning. If we can get E in similar to E out and E in to be small, then E out is small, and E out is what? E out is the error rates, the performance on unseen examples, and so on. Yeah, E out is what we want. So E out small actually means we achieved learning. If we can get a hypothesis such that E out is small, we are done. And we are one step closer to there. Okay, we need to guarantee two things. One is E in close to E out, and the other is E in being small. E in is small, small error rate on the data set we have seen. E in close to E out, okay, meaning we can do the inference right, then E out is small. Yeah, so now then we know H is close to F. We achieved learning. But is the story so good? Let's see. We only, for now, prove that this E in close to E out happens for one H. It's very important to know that it's only for one H. Given one H, your boss gave you one H, you don't know where the H is from or whatever, you just have one H on hand, and you can do the proof. Now, if you just start with one H on hand, is it learning? Think about it. We formed learning saying, we have multiple hypotheses and we want the machine to have an algorithm that picks the best one as G and so on. Now, if you only have one H, then the machine is forced to pick that H. It doesn't sound much like learning. You didn't give the machine much room for choice. Or think about it this way. If E is small for the fixed H, and A picks the H as G. Okay, that's okay. You're restricting the machine, but it so happens that this hypothesis has a small E in. Then you can guarantee that the selected G is good. But most often, if you only have one H in your hypothesis set, and your algorithm is forced to pick the edge. Whatever task you're facing, pick the edge. Okay. For example, will stock go up tomorrow or not? Pick the edge. Does the patient have cancer or not? Pick the same edge. Okay. And is the professor handsome or not? Pick the same edge. Well, most likely, if you only have one edge that you use to answer every learning task that you have faced, more often than not, the edge would not be good even on the data that you have seen. Right? You cannot imagine the same edge to answer well for the stock question and maybe for the handsomeness question. So almost always the E-in is not small. And when the E-in is not small, from Hoffman, the guarantee that you can get is probability approximately correct. G is not equal to F, or H is not equal to F. That is a super bad edge for sure, or almost surely. Okay, so if you only have one edge, it's not learning. Okay, for learning, you need an algorithm that makes choices, like perceptron learning algorithm, not forcing the algorithm to return one edge that you have used in your mathematical proof. So what we have done here is not learning. This is typically called verification, or some people just call it testing. Basically, you are providing the machines with some verifying examples or some testing examples. You assume that these examples comes from a distribution. You have a hypothesis that you want to know whether it's good or not. For example, you give your boss a hypothesis. Your boss really wants to know if the hypothesis is good or not. He asks another team to gather some examples and evaluate your hypothesis on those examples to know whether your hypothesis is good enough or not. This is called the verification flow, but not learning yet because we don't have the choice of hypothesis, which will be our next topic. Okay, questions. Okay, so can we write the inequality on another side which says the two values are close by with a high probability? Yes, and actually you'll experience that in some later lecture. Does the result on slide 20 need to be built on top of being IID? And when we don't know the real data, how do we know if it's IID? Okay, the first question. The current results that we show all need IID assumptions. It can be loosened in some way, but almost always we need something like independence. Okay, because independence actually tells you that each new piece of data provides some new information in some sense. So that's the short answer. And for simplicity, we will actually keep making the IID assumption in this class. Okay, and for the second question, we don't know the data, or we don't know whether the data is generated IID. So how do we actually know? Okay, in short, we don't know. We don't know if the data is generated IID or not, period. So in the real world, you either assume that it's IID, or you think about some possibly, for example, non-independent part of your data gathering process and try to correct that. Okay, that's the practical use of machine learning algorithms. But to make machine learning work, most likely you need some sort of independence, okay, in terms of the data you have to design your model. So that's what I call assumption, right? Remember, we say we need to make assumptions. The assumptions we're making here is that when we have IID data and some other assumptions we're going to make later, machines can do well. That's the assumption. And if you really get some data that's far from IID, for example, sometimes you get really biased data, okay, in your application. For example, you want the machines to learn a fair classifier, but the data you get are mostly from let's say the male distribution or whatever. Okay, that's a kind of data bias that's not IID from the distribution that you are interested in. You're interested in a fair distribution, while the data you gathered is not fair. And in this case, machines won't do well. And now at least we know why it won't do well, because the data do not fully satisfy the assumption. Okay. So can we choose the value of n and epsilon to get our acceptable results? N, maybe. Okay, because n is the number of data, so sometimes you use the number of data. You have the flexibility to gather more and more data to make your results better, and maybe. Epsilon is a little bit tricky because epsilon is kind of like a self-defined error bar, so it's not something by choice in general. Okay, but sometimes we use epsilon when we're trying to make some comparisons. Okay, in order to understand like how far we can be from the truth and so on. So epsilon is more for evaluation rather than a parameter for setting, while n sometimes you have the flexibility to change for that. Bad events means machine learning will give very wrong or undesired move. Maybe, but we're not talking about the move part yet. Okay, bad event actually means machines can make decisions from the data that's not representative of the true distribution that we're interested in. Okay, so that's how we define the bad event. How do you know that an algorithm have a good assumption? Generally, we do not always know, okay, but we try to think about it with our professional knowledge, with our professional understanding about the algorithm and the domain that applies the algorithm. So sometimes we'll find something that's seriously mismatches the scenario we're thinking about. In those cases, we should try not to use the algorithm or maybe modify it towards the domain. And there are also cases where we do not know and we can only maybe play with the algorithm on the application and let the result speak for itself. And is Hoffman's inequality related to Chebyshev? Yes, and actually in some sense they are very related derivations, and also one can think the Hoffman as some very special case results that we're going to use here. Is the concept we use in machine learning different from the concept in statistics? Because some terms or concept is wired in machine learning as you teach. Okay, here's the idea. Okay, many tools in machine learning are derived from statistics, and we are going to introduce them as the theoretical backbone of machine learning. It's not the only theoretical backbone, but these are theoretical backbones that are more related to our life experience, for example, on sampling and so on. So that's why we take the backbone. And however, we won't be teaching you the full picture of statistics. This is not a statistics class. And as we mentioned, statistics usually have more assumptions, okay, even more assumptions on what's happening in the process in order to get mathematically provable results. While for us in machine learning, we will just introduce the assumptions as we need without talking too much on other possible assumptions we can use to get mathematically better results. Okay, and what kind of vaccine did I have, or why am I coughing and so on? Okay, I actually had AZ. Okay, so it's definitely not the fault of the vaccine that you mentioned. But why am I coughing? I don't know. I actually had the flu shot yesterday, so maybe that's a reason, but I don't know. Okay, and sound becomes smaller. I didn't observe that, okay, on my side, but it keeps being small. Let me know, and I can try to speak a little bit louder. Okay, Okay. I also need to change to some recent questions. Okay, so is the machine learning process more first try all edge and use the verification process on each of them? We will discuss that in the next part soon. Okay, how to find the self-defined epsilon? Are there any rules? Actually, let's say this. Okay, we will see later that this epsilon parameter, if you call it, is not that useful in practice. It helps us understand the concept behind machine learning algorithms, but we don't seriously pick them in practice. Okay, so but we will talk more about those later. But trust me, we don't need to worry too much about picking epsilon. Okay, and still using the same hypothesis since for answering the question. Okay. Good. Let's move on to the next part because we actually need to teach you a little bit more today so that you can finish your Evo homework 1 as early as possible. Yay! Okay. Okay, so remember we connected learning with sampling or with the bin model by mapping one hypothesis to one bin. One hypothesis means a particular way of coloring the marbles, which are the examples or the inputs in your input space. So one hypothesis, one way of coloring, one bin. The other hypothesis, the other way of coloring, you can view it as another bin. Okay? It's not really independently another bin, okay? Because marbles from different bins connect with each other by having them as the same X and so on. But basically, to consider multiple hypotheses for machines to choose, this corresponds to having multiple bins. Okay, so then the question is, if from one of the bins, I get a bunch of marble on hand that are all green. Remember, green, correct? Orange, not correct. No political notion at all. Okay, this is this particular figure is made in the Learning from Data book. Okay, which is not related to the politics in Taiwan in any way. Okay, but okay, let's say we pick a bunch of green. Okay, we pick a bunch of marble from the bin and we get all green. Now what we want to know is this all green true or not? Meaning, does this all green mean E out would be all green or a lot of green or not? Actually, I hinted you that this may not be the case because if you look at this, okay, if you are unlucky, you can get a bunch of marbles that are fully green while inside the bin, nothing is fully, a majority would be orange or something. Okay, so did we succeed if we get something all green on hand? If we translate the bin problem to the coin problem, remember we say Hoffman for bin, for coin, for polling, and so on. So for coin, we can also do that. And that was exactly the exercise you played on Slido. Flip a coin 5 times, okay, and we see how many heads that we get. Okay, so here are our answers. Let's see. Okay, first of all, let me see if I can make this slightly smaller. Okay, so first of all, you see that, okay, the majority of you got 2 heads or 3 heads as expected. Okay, simply because those are of higher probability, right? Okay, so this is similar. If you think about every of your coin being close to a fair coin, so the new is or the E out is 0.5. okay, then the E in that you get should be 2/5 or 3/5. So mostly be 2/5 or 3/5, okay, which matches the results that we see here. But we also see some really lucky or really unlucky cases, okay, like the 0 or 5 that you have seen. Wait, let me see how I can show you this more clearly. Okay, like the 0 or 5 cases, okay, which are most far from the center cases that you saw. And okay, so that's the question we want you to think about. Okay, if we have a coin that gives us 5 heads, or if we give a coin that gives us 0 heads, is the coin really magical? If I flip a coin again, let's say I get a coin, okay, this 50%, okay, a little higher than expected. But let's say I get this 5-head coin, and then I flip the coin again. Do I really have a higher probability of getting head? Right, so that's the question we're thinking about. If I select the bin, the hypothesis that give me all green on the data, like the perceptron learning algorithm outcome, right? Classify all the existing data correctly. Will that hypothesis be able to classify the next example correctly? Is that coin, or is that hypothesis, or is that bin really magical? Is that bin, does that bin really contain more green marbles than other bins? That's the question we want to ask. And the short answer that you can see from this particular experiment that you've done is no. The coin may not be that magical to begin with. The fact that we see this is simply because we have a class of size 400, or actually we have an online class of size 100 or something, but enough to make the story, because okay, even if all coins are fair, the probability that one of the coins result in 5 heads can be really, really big. Okay, so basically, it tells us something. What you see is not the truth. You see something fully green, you run to that saying, oh yeah, I love fully green. Okay, not politics at all, but that's not the truth. Okay, the truth is that particular bin may not contain that many green marbles. That's your illusion. And your illusion is because you get a bad sample. A bad sample meaning E in and E out is far, in and E out are far away. We cannot make accurate estimates about what's happening outside. And the bad sample probability is small. But if you have multiple bins, then things can get worse. And getting worse, okay, like what we have observed here, when we have multiple choices, tells us that machine learning is not that easy. So what's a bad sample? For example, what we have observed is E out is half, but getting all heads, in equals 0. That's bad. And for one hypothesis, in and E out being far away is bad. Okay, so E out big, but in small, correct on most examples, but the hypothesis is far from F. Hoffman tells us that this for one edge is small. That's what we proved with Hoffman for one edge. But now we have multiple edge. One edge, the situation is like this. We want everyone to be able to understand this part, this rule, this illustration fully, because it's very important for understanding the essence of machine learning. For machine learning, what happens is like this. We assume that we will be getting data. And some data will be good, some data will be bad. Okay, so here, each of this is a data set. Okay, it's a sampling of the marble, a sampling of, let's say, 20 different marbles from the bin. Some of them are good meaning it can tell us something within the bin. It can let us infer what's within the bin correctly. Some of them are bad, meaning whatever information it shows in that sample is not representative. Okay, so imaginarily, we can have very different data sets. Some of them are good, some of them are bad. And what Hoffman tells us is that if you are very patient and sample data set by data set, then the probability that you get a bad data set is small. That's Hoffman. We don't actually do this sampling. Okay, that's one thing that we want to emphasize. This is imaginary. Hoffman tells us, imagine you sample dataset 1 with 20 examples, you sample dataset 2 with 20 examples, you sample dataset 3 with 20 examples. Imagine you continue with all this. The probability that you are unlucky, you get a bad dataset, is small. That's Hoffman. Okay, so understanding this for one hypothesis will extend it to multiple hypotheses in the next slide. Hoffman tells us bad probability, one hypothesis, small. Okay, so some of the datasets are bad, some are not. In total, the probability of getting a bad is small. Now, let's think about what it means to have good data for many hypotheses. Okay, and let me just directly show this to save our time. Okay, now let's say we have some hypotheses on hand. We have H1, H2, H3 up to Hn, big N. And I'm going to first assume that this big N is finite. So bear with me. For example, let's say we have 300 hypotheses on hand. And so 300 hypotheses. Now, if we continue with the imaginary process for each hypothesis, there are data sets, okay, that do not tell us the truth about the hypothesis. Okay, that's the data set is bad for the hypothesis. So every of this row is just Hoffman, but different data sets may have may be bad for different hypotheses, or different hypotheses may be bad for different datasets. Okay? Bad meaning whatever we observe on the dataset does not tell us the truth about the underlying process, does not tell us the truth about the underlying bin. There are bads here. Now, stop talking about bad. Let's think about what it means to be good. Good actually means this dataset can be used for any hypothesis. Okay, for example, there is this super magical dataset here. Okay, that is good for H1, good for H2, good for H3, blah, 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 good for Hn. Okay, so it can be used to verify any hypothesis. Think of this data as super powerful. Okay, it just has the right combination of every kind of point to verify any hypothesis, at least any hypothesis we see here. But there's no bad. Okay, bad yin and yang far away. There's no bad being good. On the other hand, what do we mean by a bad data with respect to many hypotheses? If one of them if it is bad for one of the hypotheses, then we call it bad. Or for example, okay, it's bad for 3 hypotheses. Okay, therefore it's bad. This is bad for 2 hypotheses. Well, it's bad, and so on. Okay, so good here, bad other places. Okay, so for many hypotheses, we call things to be bad if basically that particular data set is bad for some of the hypotheses. Now we're disclaimer. We only have one data set on hand, right? We say the generating many data set is an imaginary process. So we don't really know if the data set on hand is bad or not. We generally do not know. In the real world, we don't know. You just have one data set. You don't know whether it's good or bad. However, what Hoffman or this kind of theory guarantees us is that the bad probability is small. When the bad probability is small, then you can pray for good luck. Right? Okay, much like when we're flipping a coin, right? Okay, we know that the probability is small if we flip a coin 100 times for estimating its head probability. Okay, so we flip 100 times, we believe we are of sufficiently good luck and move on with the inference. Here, similarly, okay, we bound the bad probability. We want the bad probability to be small. Then we pray for good luck, meaning for whatever dataset I have on hand, I must be lucky enough to use this dataset to make inference without too much trouble. That's what we do. So how do we derive the bad probability for many datasets? And I'm highlighting this with orange here, okay, for many hypotheses. By the definition we make in the previous slide, being bad on many hypotheses meaning being bad for one hypothesis or for the second hypothesis or for the third hypothesis. So there's the or here. Okay, as long as the dataset is bad for one of the hypotheses or for some of the hypotheses, then it's bad. Now, how do we derive a bound for this kind of OR? OR is hard to operate because OR can cause overlapping and so on. But luckily, now we're just doing upper bounding, so we can more flexibly decompose the OR into probability summations. Okay, so basically this is using just considering this event separately as if they are not overlapping by OR. Okay, so this is the worst case. The worst case of several OR is that they are not overlapping. So we can decompose them, and after decomposing, that's just bad probability for one hypothesis, and we know that. Okay, and this decomposition is usually called the union bound. After union bound, we plug in Hoffman. And then after plugging in Hoffman, you see that basically we still have some guarantee, but this guarantee grows by n. N is the number of hypotheses that we're considering here. So as long as we have a finite number of hypotheses, we can derive this bound. This is usually called the finite bin version of Hoffman. Similarly valid for all n and epsilon, and now with n, the number of hypotheses. It does not depend on any ER, similar to the original Hoffman. We don't need to know them. We can still make all those F and P unknown. And basically, if we think about this bound, as long as your algorithm selects any of the hypotheses within the hypothesis set, we have peg guarantee. Okay, and this is actually, I'm stating this in a weaker version. Actually, E in H is similar to E out H for any H in the hypothesis set, or this similar is in the peg sets. So for every hypothesis, so this is what we mean to be good, right? For good, every hypothesis E in and E out are similar for every hypothesis. Okay? Then, regardless of what algorithm you choose, you know that your E in and your E out are connected. We're using this statistical tool to make them connected. Okay, then the most reasonable algorithm that you can think of is to pick the lowest E in, because if every E in is similar to every E out, then we should pick the lowest E in to get approximately the lowest E out. And that's what PLA does. Except PLA is working on an infinite number of hypotheses, while for here, we're talking about a finite number of hypotheses. Okay, but this is better than nothing. Okay, in some sense, we now know for a finite number of hypotheses, what we can do is to ask our algorithm to pick the lowest E in one, with the hope that our E out would be small as well, with a high probability. And this is the new learning flow, okay, that we learned today. And I'm going to finish this slide and then go to the Q&A. And this tells us that if our hypothesis set is finite, n is large enough, then for whatever hypothesis picked by A, we have E in close to E out. That's the multiple being Hoffman. And if A finds an hypothesis with E in close to 0, then there's a PEC guarantee that E out is close to 0 as well. So we completed our statistical learning flow where we can have a hypothesis set, albeit finite. Okay, and we added an assumption to our original learning flow by having an unknown probability distribution that governs how we generate the training data and the test data. And by this, we connect the two together by saying, we can guarantee E out to be close to 0 by these two, you can say, approximations. During training, we run PLA algorithms or other machine learning models to guarantee something like this. We guarantee E in to be small or close to 0 or whatever. We will learn later. And during testing, we connect the two by something like multiple being Hoffman to guarantee that E in is close to E out. That's the statistical learning flow as a foundation of machine learning. Okay, for today's class, we're going to stop here, but let me answer some Slido questions if there are any. And I'm going to use the recent mode to make sure that we capture the last minute ones. Okay. Do we need to? Okay. Finite hypothesis means we can enumerate all the hypotheses. Finite hypothesis means the hypothesis set is of finite size, and yes, that essentially means you can enumerate if your number of bits is high enough. Okay. In fact, we will find that n will be infinite, so it's not tunable. Oh, yeah, by the way, that's a very good comment. Actually, for now, we assume things to be finite, okay? But for the next part of the lecture, we're trying to extend this kind of analysis to the infinite case to really solve what we're facing in, for example, perceptron learning algorithm. Okay. Do we need to memorize all the mathematical formula, or we just need to understand and have the concept so we are able to do well when using machine learning? Okay, if you are on the application side of machine learning, most of the time you don't need to memorize the whole formula, okay? But there are different levels, okay? For example, you can be a pure user and just tune your machine learning models as if they are a black box or a gray box to you, but also you can be a machine learning scientist where you may need to modify the models, and if you are going to modify the models, then you need to at least know the mathematical formula behind the model in order to do proper modification. So we tune 3 parameters m, n, epsilon for a good machine learning algorithm. Several things. Okay, epsilon is, as mentioned, typically not tunable. Okay, but we sometimes will use epsilon for evaluation purposes. N, or in the future, we'll extend m to infinity, so we will have some other values that replace that. Is one of the most important things that for tuning machine learning, and we will discuss more about that. And n is a little bit tricky because more often n is given, you have a data set on hand, and you can go gather more data, but arguably it's not tuning. Okay, it's just trying to make your algorithm better and better, and we will discuss why increasing n typically makes the result better in the future. Okay, why does the okay, this is a very interesting question. Why does this goodness or badness of sample depend on the choice of edge? Okay, wouldn't sample be good if it represents the data D? Okay, let's say this. Okay, first, there's no true data D. Okay, well, the universe that we are considering is the relationship between x, y, and so on. So you can think there's a big universe, usually infinite-sized universe that we want to approximate. And we want our data set, okay, to be a good representation, to be representative of the universe. Okay, so what we're trying to approximate is the universe, not the data set. The data sets we already have on hand, we have no control of that. The universe is what we are trying to approximate. But to approximate the universe, okay, we cannot approximate every possible detail of the universe. It's just impossible. There are infinite number of bits that are needed to approximate the universe. So for our purpose, what does it mean to have good approximation? A good approximation means to be representative on every hypothesis that we try to consider. So that's another view of what we're doing here. We want to approximate the universe. We want to get a data set that approximates the universe. We cannot do that if we want to approximate every detail of the universe. So we say we just approximate the universe with respect to the hypothesis that we are going to consider. And that's why the hypothesis, okay, helps us define what it means to be good or bad. Okay, so if n grows bigger, n needs to be greater as well to make E in minus E out small? Yes. Okay, so in general, yes. If n grows bigger, you need a bigger n to knock it down, and we will discuss this more later. If we have good data set, how can we know which hypothesis is better? If you believe that you have a good data set. Of course, most of the time, we don't know for sure. You can only believe. If you believe you have a good data set, then as mentioned, the smartest strategy is to pick the lowest E-in hypothesis. Right? A good data set just tells you E-in and E-out are close. And your goal is to get smallest E out. So the best you can do from the data you have on hand is to pick the hypothesis with the smallest E in. Okay, that's basically what this theorem tells us. When will the homework be uploaded? In a few hours, if I'm not too exhausted, basically. Okay, that's most of the questions that I think I can answer online. Sorry that we're a few minutes late. As mentioned, we'll announce the homework in a few hours and enjoy them. Make sure that you ask the TAs lots of questions to complete them. What we teach today actually covers almost all, if not all, of the contents that you need for completing the homework. We have a small unfinished part, but that's mostly for summary and giving you a preview of the next part. So that's not super important for completing the homework. You should have all you need to complete the homework, and good luck. Okay, thank you. Bye-bye.